So today we're very happy to have Radu Roiban visiting us, and he's going to tell us about super translations from scattering.
Thank you very much. Thank you very much for the invitation. It's great to be here. It's great to be back. The talk is based on work done with Asad Al-Khidir and Donald O'Connell, and that builds on quite heavily on work done earlier with Donato Bini, Thibaut Damour, Stefano De Angelis, and Gerali Kron, Yaron, Eden Herdushi, and Nathan. So infinity is a complicated place, especially in gravitational theories. In particular, it has, it exhibits symmetries that preserve an asymptotic Minkowski space, for example, and also preserves the fall of the metric coefficients as one takes the distance to infinity. The version 0 of the plan for the talk today is to explore these asymptotic symmetries with on-shell fit or field theory method. And for that purpose, we're going to focus on the gravitational field and obtain other observables from it by some means. All right, so I said the word observables and gravity in the same sentence, so somebody might complain that there are no local observables in general relativity, and they would be correct. There are, however, a collection of proxies to that. In particular, the S matrix is something, it's a good proxy to that in asymptotically Minkowski space. There are, of course, no local things in the bulk, but there are sort of local things on asymptotic. In antidesiter space, there are boundary correlators that play roughly the same role, and more recently, a lot of attention has been paid to final state expectation values, and this builds on work by Kassor, maybe, and O'Connell, and also work by Hoffy and Sebastian and Simon Caron, Mathieu Giroux. And all of this, in fact, builds on much earlier work on QCD, where they were known under the name of event shapes. They're not exactly the same, but pretty closely related. These things have all fairly desirable features. For example, they are gauge invariant under small gauge transformations. And most of the time, they are IR safe, though not all the time. And as an example of something that's sort of IR safe, but not quite, is the asymptotic field. Right? So here, what you see on the screen is an animation of the asymptotic metric, really asymptotic metric, the thing that falls off as 1 over x, that happens when you scatter at leading order two particles that go along the y-axis, that go along the z-axis. The colors are the part, this is one particular polarization of the physical part of the metric, it's the part that messes with the angles at infinity. So red is less than 90 degrees and blue is more than 90 degrees, and Minkowski space is green. All right, so this happens to not be an IR safe quantity, but it can be made IR safe by a certain redefinition of the origin, but it is nevertheless invariant under small gauge transformation. So
can you clarify the redefinition statement?
Yeah, it will become clear in about 15 minutes or so. But yeah, the idea is that there's an infrared divergence, and it so happens that it can be redefined by shifting the origin. So let's talk a little bit more about this particular field, especially because this little discussion is going to reveal a couple of issues, and the point of the talk will be to connect the two, perhaps shed some light. So this is the asymptotic linearized gravitational field, right? It's garden variety expansion in terms of creation and annihilation operators. Though at this point, we say the words it's infinity, but we don't actually enforce that in any particular way. So let's enforce that. So there is a sort of a procedure that, sort of a standard procedure that follows. And it's the same as the multiple expansion in quantum electrodynamics. So anyway, there is a saddle point approximation in the process. And in that saddle point approximation, there is an assumption that's made, namely that the distance at which this field is observed times the frequency of this field is much larger than 1. Otherwise, the saddle point approximation, which I guess I didn't write fully, but it involves this factor here and this factor from a delta function enforcing the on-shell condition of the graviton. So otherwise, the stationary phase approximation simply doesn't work, in the sense that it doesn't officially apply, so one should include further corrections. However, this assumption is evil in the sense that it doesn't always apply in physically relevant situations. And one is sketched at the bottom here. We have two particles that are sort of stationary, but not quite. They move, they scatter, and then they go off in different directions. And the initial metric is sort of like this. The other one, the final one, is sort of like this. They're both almost stationary. Therefore, they must differ by modes of graviton modes of arbitrary low frequency. Another way of saying this is that there is gravitational memory, and that leads to a constant departure at plus infinite future time relative to the past, and therefore that is essentially a very low energy mode, essentially a zero energy. And it's these modes that we're going to worry about. All right, so this is issue number one. We have the standard procedure to compute fields at infinity, but they work, but they don't always work because of this. Another issue is that even though this field is invariant under small gauge transformations, it's not necessarily invariant under large gauge transformations. In asymptotic Minkowski space, these are usually referred to as BMS transformations. So here it is a lightning review. Pretty sure everybody in this room knows a lot more about BMS than I do. Nevertheless, a 2-minute review probably won't hurt just to set up notations. So
let me understand.
Yeah.
So these normally are not, they're large gauge transformations, but they are supposed to be physical symmetries of the theory, right? So the fact that they are not invariant.
yes, it's a good thing. Well, it's not an unusual thing. It's not a bad thing. Let's put that.
Right. Does not mean that's not the physical observable.
No, absolutely. Okay, just to clarify a little bit, we're going to connect these two. The zero energy modes that appear here will end up being connected to this BMS, to a particular BMS supertranslation. Right, so BMS transformations are usually discussed in the so-called Bondi gauge, which is summarized here. These are the gauge conditions, and the various metric coefficients are assumed to fall off this way. Einstein's equations connect the various coefficients here. I am not writing all of them, just the two that are essential. The shear is one important quantity, which is the 1/r corrections to the metric on S2. And the so-called Bondi mass loss, which is the change with the retarded time of the coefficient of the du squared. And it turns out that everything is determined at least at this level by the shear. So the BMS symmetries or the BMS transformations preserve this retarded Bondi gauge conditions and also the assumed scaling of the various components. So basically what they do, at least the supertranslation, what it does is it shifts CAB by some amount that looks like it. And there's another charge associated to these supertranslations, and this is what it looks like in terms of the parameter. Right. So the moral of this is that pretty much any observable that depends on the undifferentiated shear, undifferentiated with respect to the retarded time, will be sensitive to this to the so-called BMS framework, the choice of CAB. So in particular, there are zero energy contributions. There are zero energy contributions to CAB, then observables will be bad. All right, so this is a more expanded version of the plan. We're going to review a little bit the observable-based formalism, and we're going to discuss two examples, leading order, next to leading order example in which these zero energy modes and the BMS supertranslations come in. And then we're going to resum all these contributions to all orders in perturbation theory. We will see that there is a certain coherent state that takes care of all of them. Based on this, we're going to construct a charge that commutes with the S matrix. And using that, we're going to discuss the asymptotic field in more details and see how a change in BMS frame will affect the asymptotic field to higher orders in perturbation theory, essentially to all orders. Then we're going to talk a little bit about the angular momentum in the field, which is not one of the EMS invariant observables. And then also we are going to try to connect these charges that we construct here and the usual nether charge that appeared on previous slide. This one. And then we'll conclude with some perhaps unusually cheerful conclusion. Right, so the observable-based formalism, we're going to get to it in a second, but everything that I'm going to say refers to applies in the classical limit because we're trying to connect to classical GR ultimately. So let's spend two seconds talking about that. There are many classical limits that one can take in pretty much any quantum field theory. We're going to take the limit in which the various bodies are large and their various charges are large. This is in agreement with the correspondence principle. So charges would be like angular momenta or angular momentum, and this implies that the classical expansion is ultimately an expansion in the ratio between the momentum transferred between the participants in a scattering process or in pretty much any other process and the characteristic momenta of the process. If one mixes this with the fact that, say, the Newtonian potential is a classical object, and therefore any power of it is a classical object, then one concludes that there is a tiny piece of pretty much any S-matrix element that contributes in the classical limit. This is how it depends on the transferred momentum. Therefore, pretty much all loop amplitudes will contribute in the classical limit. Furthermore, if one thinks about Bremsstrahlung and the fact that it's a very classical process, one concludes that if one allows a process with an arbitrary number of gravitons or mediators in general in the final state, it should have exactly the same scaling as with this structure.
Sorry, what is Q? I'm trying to figure out what is Q.
Yeah, so Q, I'm sorry, I keep pushing the wrong buttons here. So Q is the momentum that's being transferred between the participants in the process. So for a scattering process, it's literally Q squared is the T.
Q squared is?
Q squared is the T parameter, transfer momentum. All right, so basically we're going to look at, for example, 2 to 2 processes and expand in T over S and keep this particular ratio Q to this particular power I minus 3 divided by a mass, for example, to make it dimensions. All right, so so the same scaling should occur if one has mediators or gravitons in the final state. If these mediators have momenta of the same order as the momentum transfer, and this is in fact quite reasonable. If one were to emit gravitons of much higher energies, then a body will not move smoothly. It will start having a very giant trajectory because it means if the energy that's emitted is of the order of its own. So with this, the observable-based formalism in the classical limit uses this limit, but in general, it defines observables as the difference between expectation values of suitable operators in the final state and initial state. And the final state is connected to the initial state by evolution with Resummation. O is, again, a suitable operator, typically referred to as measurement function. And it can be pretty much anything that one might consider measuring, like the impulse of a matter particle or the momentum of the outgoing radiation, or the angular momentum operator, or as it was illustrating earlier, the gravitational field, which again, in this large distance approximation is here. So the gravitational field at infinity would look like this. So it's roughly a difference between an S-matrix element and something that one might refer to as a first cross-section. Right. So let's look in a little bit more detail at what kind of contributions enter in each of these two terms. So this is the first term, which had an A here, so an annihilation operator. Therefore, here I wrote it as literally as an S matrix element by letting A act on the out state. So this is a regular 5-point amplitude in this example, and the second term is, like I said, a dress cross section. So the product of two S matrix elements with something that is in the middle, and in the middle here I have this A, which creates an outgoing gravity. This is the wiggly line that sort of ends nowhere. The dashed vertical line is the asymptotic future. Okay, so there are two kinds of contributions to any one of these two parts. One is a connected bit. Here is just for illustration of one loop contribution, but there are also disconnected pieces like this one at for the 5-point amplitude, and like this one. This is not literally disconnected because it's connected over the final state. However, it does have a disconnected piece. So for the sake of for the next 45 minutes, I'm still going to refer to it as disconnect. All right. So as I was implying earlier, and to get back to your question, this is not infrared safe, but it can be made finite, of course, by regularization. Dimensional regularization works just fine, or it can also be regularized by finite distance or by pushing this gravitational off shell, if you wish. There are infrared divergences that come from different sources, and each of them have a physical interpretation. And last but not least, and perhaps very importantly, whatever comes out through the available overlap with GR, it agrees with everything that people computed in GR. So this is ultimately correct. We're just trying to understand bits and pieces that go into this concept. So let's focus on, since I harped on zero energy modes earlier, let's focus on the zero energy modes. And first, the simplest ones, the ones that appear at tree level. So at tree level, there are these guys, just one particle doing nothing, the other particle emitting one graviton. Of course, this is for real kinematics, this is kinematically forbidden, at least for generic momenta, but of course it's not kinematically forbidden if one allows special momentum configurations, such as zero energy outgoing particles. This is the only solution to the on-shell condition momentum concentration. So the question is, what should one do with this? Should one keep them or should one ignore them? Well, there are two tracks, so let's see. There are arguments for each of them. Well, an argument for ignoring them is that we always ignore them, right? Whenever we compute S matrix elements, these are disconnected pieces. We always toss them away because momentum is conserved, not globally, but separately in two parts of the process. So one might consider ignoring them again. An argument to not ignoring them is that, well, yes, it's certainly true that they are localized on special momentum configurations, omega equals 0 in this case. However, if one Fourier transforms to position space, this would just be a constant metric. And for example, the Schwarzschild metric is a time-independent metric. So is that a trivial thing that we should always ignore? It sounds like we should. So, what should we do? Well, in this case, it turns out that the two options are in fact connected, and they are connected indeed by a BMS transformation, as was shown by Veneziano and Minkowski some time ago. So one can choose ultimately what to do, as long as one makes a consistent choice and does the calculations consistently afterwards. So if one decides that one should ignore them, this is typically referred to as the canonical BMS frame. If one chooses not to ignore them, this is typically referred to as the intrinsic BMS frame. And a supertranslation with this particular parameter connects the two. Here, U is just the ratio of momentum by mass, is the velocity of each of these particles, and M is the direction. Is the point on S2 at which one observes the gravitation.
Can I think of this as the choice of asymptotic shear?
Yeah, it is exactly the choice of asymptotic shear. For this one, the shear is zero. For this one is basically this.
Like standard Schwarzschild coordinates would set the shear to zero, but then.
Actually, standard Schwarzschild coordinate does not set the shear to zero. Standard Schwarzschild coordinate sets the shear to this one, right? Because this is basically this. Let's forget the second part, but just one part of it, right? So as one tries to solve perturbatively for Schwarzschild, one starts with the stress tensor and then iterates Green's functions upon Green's function. This, the top here, or this is exactly the stress tensor of a particle. So that's really the leading term in the construction of the Schwarzschild. More questions?
Yeah, sorry. So the usual argument to not ignore the delta functions that if you look at the Klein-Gordon inner product or the symplectic inner product, there is a mode that has zero norm, which is the 1/omega mode, soft mode. So that actually pairs to delta omega because you integrate over omega and there is an omega coming from the measure. So how is this compatible with the fact that you can just turn it off by a BMS frame?
So this is not the soft radiation. This is.
No, it's a conjugate. It's a conjugate to the 1/omega.
I don't actually know what that 1/omega mode is. But
Usually we refer to the 1/omega mode as a memory soft mode. It's Fourier transform to a step function.
So this is not entirely connected to the memory, though it does, of course, the memory is something that appears here and it is one of the, I would actually call the memory as a zero energy mode because I'm independent thing. I don't think it will affect what I'm going to say later, so maybe we can chat about this after. However, the idea that the point is that, so if everything were related with just constant contributions to the metric, there would be very little to say. I should stop here. However, as it turns out, these zero energy contributions, they also contribute things that are time dependent. Not at this order, but at the next order. So to actually figure out exactly how to do this, one has to figure out how to include these zero energy modes, for example, in loops. So there are several options. Perhaps the cleanest one, though it requires some further formalism to be developed, is to put the final state at some finite distance and define creation operators there. This introduces natural cutoffs. It would move these zero energy modes off zero, and it will allow one to track them. Anyway, it requires some further development, so we can't use this. Another option is to push gravitons off shell, and this was suggested, I think, by Hoffman and collaborators. This is interesting and very interesting, in fact, for discussing the metric, the scattering metric, or in fact, any metric sourced by some process at finite distance. It introduces a natural regulator, which is the off-shellness of the graviton. However, the small gauge invariance is lost. Of course, this is not a problem because the metric at finite distance is not invariant under small gauge transformations. Nevertheless, if we could avoid this, perhaps we can try. An option that's closely related to this was proposed by Pistas and Para-Martinez late last year. And the idea is to inject, in general, some momentum in this measurement function and define the form factor instead. And for the asymptotic field, it's essentially the same as pushing the graviton off shell. So we're not going to do this because trying to avoid breaking the small gauge invariance, but we're going to keep the gravitons on shell and push something else off shell. There is no free lunch. You can't have everything that you want. And we're going to push the matter off shell. Right, so here's what happens at next to leading order. So the idea would be to take these guys that we just talked about and think of, unitarity, they should also contribute to this dressed S matrix part of the observable. Here, this dashed line indicates the graviton that has zero energy, so it's this one, so on the right side here. So because this is zero energy, it's really only the zero, it's only the strict soft limit, the leading soft limit of the 6-point amplitude that contributes. in particular the red term here. And a little bit of work suggests that implies that the contribution of this term looks like this. There are two integrals that are the same up to the labeling. So this is formally the integral. The question mark is there because by itself the integral is ill-defined. So one has to regularize it by some means. Like I said, we're going to push the matter off shell. So we're going to shift this momentum P2 by some amount that's connected to the actual outgoing graviton. And with this, there is,
Can I ask a
yes,
question?
of
What
course.
confused me a little bit about this is that I feel like you can do it in both directions. You can make it heavier or lighter. So if you make like the outgoing particle lighter, the one that goes with the graviton, then you get support for this diagram, but it's like
that
almost
is
like
correct.
a
Yes.
heavy side theta function that it kind of
Yes.
turns on depending on,
That is correct. And
How
we
you-
puzzled over this for
Yeah.
a long time. If you wait maybe 15, 20 minutes, there is another version of this. So here we chose it such that it's non-zero.
Mm.
And we had at the time we had a very good reason to choose
uh-huh,
to regularize this so that it's non-zero. The very good reason was that we were comparing with GR calculations and we wanted to match them.
yes,
And if you make it zero, then you don't.
yeah,
So it turns out that this integral can be computed by pushing this k off shell
yeah,
and keeping the matter on shell. And by doing that, you get up to matching the regulators. The result comes as if this one is pushed the right way to be non-zero. We'll get to that.
Could you briefly say why the integral is not well defined?
So just on scaling, as you scale L to 0, there is basically P4L over L to the fourth. There's a logarithmic divergence.
Okay.
And the logarithmic divergence, so with this regularization, right, so beta is the regulator. So there are two regulators here. One is the dimensional regulator and the other one is beta, the off-shell. So evaluating this integral produces two divergences, in fact, one fixed by din reg and one that's fixed by beta. All right, so putting all of this together and adding the leading order part, and this really hopefully answers your original question, where the divergences go. So the metric at infinity becomes this. So this is the 3-level part, and the reason it appears here is because of the soft limit. And all of this discussion fits into a coefficient of this leading order. So at this order, 1 minus x is e to the minus x. This x here has a constant, and this constant involves this 1 over epsilon. But because of this factor of omega here, that 1 over epsilon fits straight into x0 minus x, into retarded time. So by shifting the origin of the retarded time, it's fine. All right, so this is the one loop story. The idea would be, does this exponentiation work as I tried to make it work here? 1 plus x is e to the x. Or are there problems? So the idea would be to attempt to resum all of this stuff and rather to resum all the zero energy contributions and see where they go. But the other thing that I would like to emphasize here is that the divergences went away. But the other bit that's worth emphasizing is that this t here, which is this combination of logs, which is angle dependent, direction dependent, that also wants to sit with the retarded time. So it looks as if it can be removed by a shift of the retarded time. And that's the connection between the zero energy modes and BMS transformation. So this T really wants to be absorbed, or for example, if one chooses to absorb a shift the retarded. All right. So beyond one loop, things get a little bit less transparent, so to speak. But the idea is to first identify the classical contributions of the zero energy modes, and ideally identify the classical contributions that are not part of a continuum of modes. So not things that, for example, in a loop, there is always a zero energy contribution, but it's really part of a continuum. Because of the loop integration, we would like to identify things that that literally want to sit at zero, at zero frequency. So this is a counting of classical contributions in these in this dress cross-section part of the calculation. And these in here, there are, like I said, zero energy contributions, but they're all part of a continuum.
So can I ask, by
Yes.
just cross-section, you mean inclusive cross-section?
No, sorry, I'm referring to it's a little bit of a misnomer. I'm referring to it as a dress cross-section because it looks like an SS diagram with something in the middle.
Ah, I see, okay.
It's not literally a dress cross-section because there is, in this particular instance, there's this graviton floating about.
Yeah.
But if this were, for example, the impulse calculation or
Yeah.
the radiated energy, so that would literally be a dress cross-section. Because it's the same S matrix on left and right, and it has an operator that sits on any one of the lines.
Can I understand the divergence is coming from the fact that you're calculating a scattering, but you're not matching the the shear at early times to the shear at late time. I mean, you don't have the right supertranslation frame, and then you're trying to find the right outgoing frame to match the incoming frame.
No, not really. There are several kinds of divergences. I glossed over two of them and I focused on the one that appears in this particular bit of the calculation. So there are two more types of divergences which literally fit in exactly the same mold as this, but they have different origins. So there's let me backtrack for a second. So there are infrared divergences related that appear straight in this part, in the amplitude contribution here, and these are they are related to the long time propagation of the outgoing graviton in some background metric. It doesn't have to be it's still a time independent, but it needs the entire Schwarzschild parts to get the right answer. There's another infrared divergence that comes out of this. And here I'm basically parroting what Hawking collaborator said. There is another contribution that comes out of this, which has to do with the fact that the incoming particles don't come in straight, but they are slightly deviated, again, because they don't propagate freely, they propagate within in the long distance field of the other particles. Both of these contribute to additional divergences, and they both end up proportional again to the leading order metric, to the leading order asymptotic metric here. And they have exactly the same phase distance. But it's not necessarily related to the supertranslation. We can talk about what.
How does this discussion relate to the choice of shear that you were trying to make earlier?
The relation to the choice of shear is that, so if we absorb this, if we exponentiate this object T here, so T has also an angle dependence. So if we keep these zero energy modes in the calculation, then we have this explicit T appearing in the exponent. If we don't, then there is no origin for this T, but one can restore it, one can match the two calculations by shifting the retarded time by this amount, and that changes the shear, and that's the connection.
Is that equivalent to the Veneziano
Yes,
connection?
it is. Yes, it is exactly the same.
Yeah.
This shift is exactly the same as Veneziano property. And this is in fact a nice consistency check because it fixes the waveform, the asymptotic field, and at the same time it fixes the radiated angular momentum.
I see, so all of these are connected, so you can apply kind of the time shift of Veneziano. And that's equivalent to kind of.
We are going to get to the radiated angular momentum, I hope. Okay, so the left side, getting back to the counting, the left side of this panel doesn't exactly have the zero energy contributions of the zero energy modes of the type that I was describing. They are all part of a continuum. However, there are some that appear also from sort of disconnected type contributions to this cut part of the observable-based format.
So, sorry,
Yes.
maybe one question. Can you renormalize this new divergence to achieve some resummation?
We are getting there,
Okay.
but yes. So this divergence, again, this is in this particular example, in this particular one-loop example, all these new divergences, they sit in this constant, which is constant of epsilon and beta. And that is a reasonable, a non-BMS type shift of the origin of the retiring time. So yes, everything is in fact finite. Otherwise, I couldn't have shown you the animation on the first slide, but well, I could have just not.
This is the analog of this rapidity divergence.
Yeah, that is awesome. Right, so it turns out, so cutting to the chase, it turns out that contributions of this type, in which there is a connected S matrix element on one side, and one of these sort of disconnected but not disconnected S matrix elements, but with only one particle. An amplitude, an S matrix element that looks like this, one particle coming in and many particles going out. These, in fact, contribute exactly to what we might want, provided that we can argue that this particular amplitude or this particular S matrix element has a scaling with the momentum transfer that is super classical, that is stronger than classical. You might wonder how exactly is that really possible. There's nothing over classical, so it's nothing more classical than classical. However, it turns out that such things exist if one also restricts to these special momentum configurations, specifically the zero energy kind. So here's an example of the Compton amplitude. There are typically three diagrams, three-level Compton amplitude. There are three diagrams. The important part comes from the first two. The third one, just by inspection of the momentum transfer between matter and the gravitons, one finds that it scales like q to the zero. But there are two graviton momenta in here, and 1 over q squared from the propagator, so that's q. The only place where things could go off the rails are in the first. So I'm writing here generically a stress tensor for this coupling and another stress tensor for that coupling. And they depend on Q, the momentum of the in and out gravitons. If one expands in this Q, one finds to leading order that there is an overall factor of 2 propagators. And using the Sokhotsky relation that connects propagators with different delta function, with different epsilon prescriptions and the delta function, one finds that indeed there is that the coefficient of this product of stress tensors is in fact a delta function that sets to zero, that sets on shell the intermediate propagator. And because of this, it actually scales like q to the -1. Right, so this is not the classical part. The classical part of Compton amplitude is the next bit. It's just like q. But anyhow, this is the part that we're interested in, and by crossing the incoming graviton to the outgoing one, to the outgoing state, we find this S matrix element is now supported solely on these momentum coefficients. So we are there.
Each of the terms also scales like 1 over q. Excuse me. Each of the terms also scales like 1 over q, right?
You mean separately? Each of them? Yes, absolutely. Each of them scales like 1 over q. But the important part here, and in what we're going to do on the next slide, is that they combine into this particular delta function that sets to zero, that sets on shell this intermediate propagator. So this is essentially the key for resumming all of it.
So what is it you call superclassical in this? This is the delta function that is
super. Delta function scales like 1 over q. Scaling q, the scales
because the subfactor is also 1 over q, and the subfactor is also 1 over q.
Yeah. So there is in fact a very close relation between the soft factor and what we're going to call. So the soft factor is in fact one of the two factors.
Right.
It's the epsilon. Right. And this is indeed exactly what happens if one goes to higher orders. There's a generalization of this Sokhotsky relation that goes by the name of the aconal identity. And all in all, this S matrix element, one in, L gravitons out, and matter out, looks exactly like what you are expecting, a product of soft factors. So it's convenient for the purpose of resumming all of this to turn this S matrix element into an operator-like object. Basically dressing each of these guys with the graviton creation operator acting on the matter, on a state with a single matter particle. And in doing so, there's a symmetry factor because then one has n factorial ways of assigning momenta to assigning the original Q1 to QL to these gravitons. So all in all these states can be resummed into a coherent state that acts on the one matter particle, state. So this is called the state psi, and it's e to the I QS. QS is just an exponentiated soft factor with the graviton creation.
It's a bit like a Wilson line or.
Yeah.
What
So
are we taking for the upper limit of the integral here? Like they want to integrate presumably over.
This is, so the integral here is, the integration is over the momentum of the matter. The
Yeah.
idea is that there's a wave packet here, 5p, which will peak it around some momentum of our choice. So this integral can run over all the matter from minus infinity to infinity.
Oh, I guess then
This
what's
little
the
phi
with
of p,
the
yeah,
wave-
there is some width.
But that's presumably related to your beta parameter from before?
No, this is unrelated. It's just there for me to not write a plane wave for the matter state. It could, the fact that the width is non-zero, we're not going to use too much we're not going to use at all, in fact, this wave packet, but you are correct. It could be interpreted as being part of the beta parameter.
Yeah, I guess I meant more precisely like the limit, the upper limit of the energy of K in the QS.
Okay. Oh, that one.
Yeah.
No,
Whichever
sorry.
was
I
related
thought
by
you,
Michel's,
no, I thought you were referring to this. So at the moment, QS is still a formal expression. We still have to regularize it somehow.
Okay, yeah.
Yes, the upper limit, in fact, as it stands, the integrand contains a delta of omega. There is an on-shell condition in the phase space here, and then together with this, it will produce a delta of omega. But we are going to regularize this in the sense that this P is going to be slightly shifted by an amount that we're going to choose on it.
I see.
For the time being, though, we can ask, what does this dressing factor do to this asymptotic gravitational field operator that we started out? So by just conjugating it, one finds that it started out just creation operator and annihilation operator, so basically nothing, no background. This conjugation with this Wilson line or this dressing factor will shift it to create in the initial state basically the asymptotic field of two particles coming at each other, each with momentum P1 and P2. So literally this prepares an initial state of exactly the type that one might want in this in the intrinsic DMS spectrum. All right, so
I am sorry, one question. What if you just start with the background field method with Schwartz, asymptotic Schwartz metric, and do the same calculation? What would that do?
That would be another way to approach this, except that with the current computational abilities, it stops after one, perhaps two orbits. It gets hard. In this context, we are addressing the asymptotic state with this, and the idea is to let the S matrix do the job of actually creating the entire background metric of the incoming Schwarzschild. Okay, so I need to hurry up. So this is a summary of part one of the talk. We constructed this coherent state that addresses the incoming matter particle states, which resums zero energy contributions. And it is a displacement operator for the asymptotic field. one can think of this resummation as extracting a piece of the S matrix and putting it in the asymptotic state. Now, I argued earlier that there is a connection between these zero energy modes and BMS supertranslations. Now, one might expect that there should be a way to, because of this relation and because of work showing that the S matrix is invariant under BMS transformations, one might expect that it should be possible to modify this, this dressing factor such that it actually commutes with the S matrix. And if that were possible, then things would become a lot simpler. One would start with one of these observables. One would expose these QS that we did. Then if the initial state doesn't have any radiation, one could freely modify this QS to add the extra bit that would perhaps talk to just gravitons and obtain something that commutes with the S matrix, push it through, and then all of this song and dance would amount to some kind of conjugation of just the observable that one is.
What is the QH?
QH, I haven't told you what it is. The rest of the talk, which is going to have to be cut short in view of the time, is something that we're going to reconstruct such that QS plus QH commutes with ES. As it turns out, this combination is exactly is closely related, and in suitable circuits, it's exactly the neutral charge of BMS supertranslation. Right. So we want to modify QS so that it commutes with the S matrix. So we have to first worry what is the commutation relation of QS with the S matrix, and because QS is linear in the graviton creation operators, it means that it goes into the S matrix, it fishes out one graviton at a time and talks to it. It commutes with it in some. So to that end, it's useful to reinterpret the S matrix as an operator by adding back one graviton annihilation operator, so we can expose this commutation relation. Moreover, because the gravitons inside QS have zero energy, it's really only the strict soft limit of the S matrix elements that are important. So here is here's another soft factor that Alfredo was mentioning a little bit earlier. So all in all, there are two kinds of contributions to these commutators. One that comes from gravitons in the S matrix attached to matter particles, and one when the gravitons are attached to other gravitons, except finite energy. So in principle, one could be bold and proceed to ignore the fact that we peeled off zero energy modes from the S matrix and attempt to construct a QH such that QS plus QH commutes to the full S matrix. This is possible, but one can also restrict to just commuting with the S matrix without zero energy graviton. In that, attached to matter particles. In that case, one needs to worry only about this particular commutation relations. And skipping over that, over the matter part, this is the calculation, which is essentially identical to the one that happened at one loop. Here, the stub here in the graph says that this doesn't need to be just a 2-to-2 process. It can be attached to the rest, to some more complicated setup. Anyway, so this is the calculation the same. I'm not going to go through it again. What I am, however, going to mention is what I mentioned earlier in connection to Hof's question, that if one computes this integral like so, by pushing, by having an off-shell graviton, this is the result of the integral, and it happens to be finite, both as far as lim reg is concerned and other divergences are concerned. This is the result of an off-shell graviton, and if one takes the on-shell limit, one finds basically this, just another regulator that covers both of them. So up to mapping these two, all the meat of the calculation is the same. Okay, so where are we? We are here. This commutator of QS with S produces something, a constant basically, and that constant is attached to basically any one of the finite energy gravitons in the process. So it can be mimicked by a commutator of the S matrix with a QH, which is basically a number operator for these finite energy gravitons. And the dressing factor here is exactly this object up to some coefficients having to do with the salt factors. All right, we are done basically, and we can reap the rewards of the calculation. So for that, we have to summarize. So we constructed QS, and I didn't tell you about this. We constructed a QH0 such that this total Q commutes with the S matrix. This is QS. This is QH0. And by inspection and by counting factors of omega, the frequency of the gravitons contributing here, one can also show that QS and QH, in fact, commute with each other. So whether one writes e to QS plus QH or e to QS times e to QH, one finds exactly the same answer. Great. So in the remaining 10 minutes, let's see where this leads us. We are back to actual physics and to see how this, how everything that we did relates to observables.
QS and QH both commute with each other.
Yes, they commute with each other, and only the sum commutes with the S. So, all right, so getting back to something that I only sketched earlier and perhaps made no sense at the time. So this is, let's consider something that this particular expectation value. And so we can first break off this the S matrix and peel off QS from it, basically extracting all the zero energy gravitons attached to the incoming particle. Then if we assume that this incoming state has no gravitons of its own, then we can freely add QH, 0, because it counts gravitons, and there are none. And then we have something that commutes with the S matrix, we push it through. The S matrix stays put, just it has no more zero energy gravitons attached to matter particles. And then we get to conjugate whatever observable we have with this operator. If we look at the asymptotic field, we get two pieces. One that we already talked about, the shift due to the presence of QS, and then QH contributes basically this, whatever the coefficient of this number operator was, which is exactly what we had at one loop. At one loop, we had 1 plus x equals e to the x. Here we have the entire e to the x. So putting this all together, and here, right? So this is that we see that the zero energy gravitons literally enter as a BMS supertranslation. All right.
Sorry, so here QH is annihilating the incoming state.
Yes, I assumed that I started with an incoming state with just matter and no gravitons of any energy.
Usually we expect QH to create soft gravitons, not to annihilate. Because it's like the dagger of that.
So QS is the thing that creates.
Oh, sorry, QS. Yeah, QS is the one that you get from the whistle line.
Yeah, so this is that QS appeared because I peeled it out of the S.
I see.
QH was added for.
So QS is creating soft gravitons, and then QH is just the.
QH I can add it here for free because nominally I can add it straight next to psi, but then because it commutes with QS, it goes in the exponent. Put it anywhere else. All right, so
Sorry to interrupt, but in this context where you take something like a gravitational Wilson line that explains the QS, is there in that similar picture for the QH?
not that I know of. QH was just constructed so that QS plus QH commutes with the S matrix. And so I should stress that this step here, the first arrow doesn't hold if psi contains gravitons. So if the initial state contains any graviton.
But you're adding the QH, you say for free, but you're changing the state?
So,
Like the instant?
No, I don't want to change the in state at all.
Yeah.
So the in state is just matter particles momentum 1, matter particles momentum 2.
Yeah,
That's it.
yeah.
So on that, I can act with QH and get nothing because there are no problems. QS is not from changing the state, but it's from peeling it out of the S. I was mentioning a little earlier that there are two ways to think about this QS. That, one can think of it as part of the S matrix, or one can also think of it as dressing the state. And in the process, in this product here, I can take it out of the S matrix and put it back in the state.
I understand. So this is the S
it.
hat is the one.
Yes, the S hat is the guy with the S matrix.
The sum of these two quantities, is that the total super translation charge? So in this calculation, are you checking that essentially checking that the total super translation charge is conserved?
So QH was constructed such that this thing is conserved.
Yes.
And if I'm allowed to go a few minutes over time, I will show you that this QS plus QH, in fact, can be made to be equal, can be shown to be equal with the super translation charge that I have on slide number 2. There is a little bit of a calculation that goes in that. Right. So in fact, maybe the next thing that is interesting to look into is the angular momentum laws. But in view of the time, let me skip this, in fact, and get to the relation that you were just asking about. So to connect this charge that we constructed, QS plus QH0 with the super translation charge, which is still, or rather with the change in the super translation charge, we should take this QS and grad QH written in terms of creation and annihilation operators, can write them in terms of the natural quantities in GR, namely the shear. So there is a shear operator that one can define, which is this one. It basically goes into H and fishes out the bit of 1 over S, the bit that's proportional to 1 over X. And it's exactly the asymptotic field. So there's a little bit of a calculation, the ingredients of which are listed here in case anybody wants to reproduce it. But one can show that QS can be rewritten in this particular fashion, where F is again the shear operator, dot is derivative with respect to the retarded time, and dA and dB are covariant derivatives on S2. And T is the same T that we had before. It's the same T that appears here, and it's this P dot K log of P dot K squared. All right, so this is the fate of QS. It looks like this. One can integrate by parts these two derivatives and make them act just on the shear. QH has a very similar fate. It's bilinear in creation operators, and so is the shear operator. So in fact, up to a normal ordering constant, which we toss away by imposing normal ordering, this QH0 can be written this way. So putting it all together, the change in this charge that we constructed looks like so. And in the second equal sign, I made one tiny assumption, namely that we're in the classical limit, so we get to minimize uncertainty. So the expectation value of a product is the product of expectation value. So how does this compare with GR? Well, the change in the classical super translation charge is given by the Bondi mass loss, and I chose normalization so that the two are literally linked. So this, I hope this answers your question. This Q0 that we constructed is, upon taking its expectation value and a little bit of massaging, literally the same as the change in the super translation charge. So that basically nails the connection.
So you haven't established this as an operator equation?
No. It's not an operator iteration because specifically I need to use this. So this is true in Platinum. All right, so this brings me to my summary.
Very confused in the last slide. So usually the part would have some contribution from the matter.
Yes, this was part of the limitations that I didn't read, but yes, there should be a contribution from the matter part in here as well. And yeah.
Why isn't there then?
It's because I just didn't compute it. I did not include it.
We wouldn't expect a conservation if you didn't include the mass.
Well, that's why I also didn't say that this delta Q is zero. I said. Yes.
But there should be.
Yes, there should be, and
Matter.
there is. This is part of the 3 or 4 slides that I skipped in view of time. There was, right, so this is the matter charge contribution. There are, in which the zero energy graviton is connected to another matter particle. And anyway, there is something that now depends on the creation operator, sorry, on the number operator of the matter part. Yes, it's there. I just didn't talk about it. All right. So just to summarize, before getting dangerous to sit between physicists on lunch.
I guess my confusion was because then it will annihilate the initial state, right? So you're exponentiating the Q hard. But if there is if there's a matter part to the Q hard, then it will annihilate the initial state.
I do not. The reason I focused on the hard graviton contribution is because we didn't quite think very deeply about what to do with the matter particles, the matter hard charge, and exactly how to deal with it in this framework. That's something we're thinking.
Is there a typo? Are there two TNs and?
Yes, it is a typo. There should be just one.
So it's only linear and two.
Yes, it is linear. It should be the same as that. Thank you. All right, so we talked about the connection between zero energy modes and supertranslations and the connection between canonical and intrinsic frames. One can, of course, ask the question, can they be distinguished by observations, at least in principle? And that's a longer discussion that fits in the -3 minutes that I have. We also talked about this dual orders in perturbation theory, and we saw the connection, at least as far as the graviton contribution to the hard charge between the classical Noether supertranslation charge and what we constructed. There are a number of things that we are thinking about, namely, for example, how to include in this framework more general supertranslations. We constructed exactly one, which was why the original singular was in the title. One would hope that a similar strategy can be used to include more general supertranslations and indeed more general BMS transformations. But at the moment, we're not quite sure about how to do that. One can also ask questions about what other observables depend on the BMS frame. And we can talk about this afterwards. And last but not least, one might wonder about the effects of BMS transformations at finite distance. And this is, of course, closely connected with the previous question. But, anyway, I think we should expect more new and interesting results and perspective on symmetries in gravitational theories in the relatively near future from the point of view of the S matrix. Thank you.
It's a lot, Radu. So before we all leave, I was going to announce that there's a dinner this evening, a speaker dinner. People are meeting at 6:30, right, in the lobby. But before we go to lunch, are there any more questions?
So if you look at can you pull up the asymptotic expansion of the field, the 1 over x?
Yeah.
Right. So each of these modes do not solve the wave equation asymptotically, right? So we don't have plane waves at non-infinity. The solution of the wave equation at non-infinity is e to the I omega t minus r star, which is r minus the log of em or something. It's the tortoise coordinate.
Yes.
So now imagine that we insist on Fourier expanding in plane waves, then this log divergence would probably be absorbing in the expectation value of A. You can always Fourier expand, of course, in e to the I omega, right? but each of these modes is not a solution of the asymptotic wave equation.
It depends how asymptotic you are, right? So,
Yes, the one over R term. Yes, the
well, so the asymptotics is really Minkowski, at least from an S matrix point of view, the asymptotics is literally Minkowski, which is what this is, which is what this actually is. These are just modes on Minkowski. Now, the log R that appears in the exponent, to include that, this is actually something that we've been discussing with Ada and for quite a while. That log R can be included in this by it originates from the infrared divergences of the S matrix and of the cut part of the observable. And one can think of this as the effect of regularizing, as the effect of going to finite.
I think even if you look at just the one over R term, you cannot neglect the log of R because it's there in the. If you just look at the real wave equation in the non-infinity, it has the solution of that.
That term comes with a G.
Right.
G times log
Right.
R.
So here you're just taking the linear. Yeah, I agree that if you just keep just take the linear order in G, you will find something that looks like this. But that means that the higher order in G somehow went into the amplitude.
Yeah,
Kind of what.
that's yeah.
So
This is related to the 1 over epsilon infrared divergences that we were discussing a little earlier. For example, the 1 over epsilon that comes from just the amplitude part. Once if you regularize those divergences by pushing the graviton off shell, then that is going to produce exactly what you're saying.
right. So wouldn't it be a better strategy to start off with the asymptotic solution and then compute the amplitude for that basis instead of the
Now,
plane wave?
because again, putting G's in the asymptotic wave, in the asymptotic solutions, so putting couplings in the mode expansion will mix orders in perturbation here. So it might be conceptually better, but technically it's a pain in the neck.
Well, it seems to be the right basis though, because that's what people would compute like response functions in black holes, and the function of the black hole would be started.
I'm not going to disagree with that. All I'm saying is that those terms in a systematic expansion in G, they come out.
It's equivalent.
It has to be. There's only one bit of physics in there.
Yeah, it's always the problem. We know that some things resum, but we don't know how to incorporate that information explicitly. Right? But here you expect to have at least that series resum in the exponent.
Yeah, in fact, we can show that log R series does resum. And it's ultimately a consequence of the exponentiation of infrared divergence.
Could you I mean, this is now at the end of your slide, you just made you go to the beginning. Comment on what you meant by the action of super translations in the bulk or something. Yeah, one of your last points you made. Isn't that arbitrary?
No, it's not. Okay, so this actually goes through these organized slides. This is something that is not yet worked out, but it's not fully. So, you know, there is, as you change the asymptotic shear, the metric in the bulk doesn't stay full. It changes. It has to change because otherwise it's no longer a solution to Einstein's equation. So here is how the Schwarzschild solution changes if one allows for an arbitrary asymptotic shear, which is this CAB. This was worked out starting with Hawking, Perry, and Strominger some time ago, and then fully worked out by comparing with
Just to stop there, the metric of the bulk will depend on your coordinates and how you choose your bulk coordinates. I mean, you've chosen to evolve it into the bulk. You need to choose a gauge. And
so this is again, this is in Bondi.
yeah, but then every statement is that Bondi gauge has a considerable amount of freedom in the bulk. I mean, a huge amount of freedom, which one are you choosing?
Yeah, okay, so.
This is a reparameterization of shorthand.
No, it's not a reparameterization. It has different asymptotics.
But it's just a metric mechanically, the shorthand metric in different coordinates.
They are related by a supertranslation. So one can say yes, they are, but they're related by large gauge transformation. So related to your question, I would interpret this huge amount of freedom in the bulk as small gauge transformations because they would fall off as faster than 1/r. So those, in everything that we discussed, those guys should be irrelevant. Because we are really, in this H that we computed is sensitive only to the 1/r bit. But what I meant by the comment about EMS further out is there are observables that are sensitive to things that happen in the bulk. For example, if one were to look at the scattering angle of a particle off a Schwarzschild black hole, it depends whether one takes C equals 0 metric, which would be the standard Schwarzschild metric, or if one takes C to be something else. So that's what I meant.
That such observables should be invariant under small.
They should be invariant under small gauge transformation. So the huge here Hawking, Perry, and Strominger, they picked some version in the bulk, but I guess what I'm trying to argue is that that whatever choice they made is not relevant for the observables that can be computed out of this method, which is the type of observables that were computed.
Right, why don't we postpone further questions to offline, and thanks Radu again for an excellent talk.